Welcome back, everybody. So now we're going to prove a couple of theorems with some complicated proofs, but they're going to simplify cardinal arithmetic quite a bit. So remember we defined addition of cardinals and multiplication of cardinals a few weeks ago. Addition is the cardinality of the disjoint union, and product is the cardinality of the Cartesian product. And we proved very basic properties about cardinals, and all of those have like very constructive proofs. So it was important actually to see their proofs, because you see kind of how product and addition works. But in the presence of the axiom of choice, we get this very strong theorem, which says that if you have infinite cardinals, actually you only need one of them to be infinite, then the addition of two cardinals and the multiplication of two cardinals always gives you the maximum of the two. Okay, so there isn't too much to this. You always get the maximum and you don't increase, in the case when they are infinite. So in particular, in these cases up here, if these cardinals are infinite, you get that these both of these things is equal to the maximum of kappa lambda mu. In the case when the cardinals kappa lambda and mu are infinite, you get that all these equations up here are just equal to the maximum of the cardinals. So they are kind of all like trivially resolved, in the sense they're just the maximum. They're just the maximum of the two of them. So it was still interesting to see this theorem, even in the case, well, on the one side because you can prove this without the axiom of choice, and on the other side because these constructive proofs that don't use the axiom of choice really show you what's going on with addition and multiplication, while this one, since it's using the axiom of choice, doesn't really show you what's going on. There is, every time you use the axiom of choice in a proof, it's kind of like a magic is being involved in the proof, and it obscures a little bit what's going on, but still true. Okay, so let me make a little comment about how we're gonna go into the proof of this. Suppose that lambda is less than or equal to kappa, so that means kappa is the max of kappa and lambda. Then we get that kappa, with what we know so far without proving anything, less than or equal kappa plus lambda, which is, well, assume that lambda is at least 2, because otherwise it's trivial. So this is less than or equal to kappa times lambda. You just need lambda to be larger than 2 for that to be true, but if lambda is 2 or 1 or 0, this is trivial. And then this is less than or equal kappa times kappa, right, because lambda is less than kappa. So it would be enough for us to show that kappa times kappa is less than or equal kappa. And then we will get that all of them are the same, right? That proves the whole equivalence up there. We're still gonna do 2 steps. And we're gonna first prove that kappa plus kappa is less than or equal kappa. And then we're gonna show that kappa times kappa, just because the proof, one is easier than the other one, and so in the easier case we get to see some of the ideas without getting too confused by the whole thing, and then once we're used to those ideas we can add more things to the mix. Okay, so let's start proving that kappa plus kappa equals kappa for any infinite cardinal kappa. Okay, for a finite cardinal we know that's not true unless it's 0, but for an infinite that's gonna be true. And well, we're going to use the axiom of choice, as I already said, and we're going to use this format, the Zorn's lemma, to prove it. So how do we use Zorn's lemma? Remember, we need to define a collection of sets, prove that it satisfies the chain property, and then obtain a maximal element, and then see how this maximal element is being used. So let's do that. Alright, so let's do this proof. Okay, so we need to start defining our collection of sets where we're going to use Zorn's lemma. No? We're going to apply Zorn's lemma to this collection of sets. So what is the collection we're going to use? We use these collections these similar collections before. So A is going to be a collection of functions, first of all, these functions. The range of the collection, we are going to make it, the range of these functions, they have to be subsets of kappa. They don't need to be equal to kappa, just a subset. The domains have to be equal to the range times the union the range. So we're gonna let A be this guy. Okay, so we're gonna let A be this range, which depends on the function. So each function in the collection will have a different range, so a different A. But we ask the domain to be the union, the disjoint union of the range twice, right? So it has two copies of the range in the union, right? Because what we are looking for essentially is a bijection between kappa and kappa plus kappa and kappa, or kappa disjoint union kappa, two copies of kappas to one copy of kappa, right? That's what we're looking for. So we're gonna start with like sub functions which do that. So these functions f go from A disjoint union A to A, right? And then this one is a subset of kappa times kappa, and this one is a subset of kappa for the ones in the collection. And f needs to be 1 to 1. So that means this is actually a bijection between these guys, because that's the range. The range is everything that is used. So this is a bijection between these two guys. So they are equinumerous A union A and A. Okay, if you want to apply the subset axiom to make this, to define this, if you want to apply the subset axiom to make this definition concrete and to know where this is coming from, we need to say what is f is coming from. Well, f is a relation. I mean, it's a function. So in particular, it's a relation, a set of pairs. And the pair, so that means a subset, it's a set of relations. It's a subset of this set of pairs. What are the pairs coming from? Pairs are coming from first A union A, which is a subset of kappa union kappa, and they go to kappa. So this belongs to the power set of kappa union kappa times kappa, right? It's a function from kappa union kappa to kappa as a subset of the set of pairs. Cool, so we can define this using the set of axioms. First step is to show that it satisfies the hypothesis of Zorn's lemma. So that means you have to verify this chain property. By the chain property, I mean the fact that for every chain B, which is a subset of A, the union of the chain belongs to the collection. Okay, so that means if you have if you take a chain inside A, which means, what does it mean? Chain is a subset of A, so it's a set of functions, and all the ones in all these collections, all these functions in the set B are they have to have the right properties, right? All the 1 to 1, and the domain of each function is the union of the ranges twice. And what we need to show is that if we union all these functions together, we're going to get another function that satisfies the same properties. It's important to use the fact that these functions inside B are in a chain. The ones inside A are not a chain; they are like all over the place. But we just need to prove this for chains, where they are like just nested functions, one bigger than the other, in like a nested collection. It might not be a countable collection, and that's why this is not completely trivial. These functions might be like huge, like super big cardinal size chain, but they are still nested. Whenever you have two of them, one is bigger than the other one. That's what it means to have a chain, right? Review Zorn's lemma if you don't remember that. Okay, so let's check on these properties. First, we proved before already in another application of Zorn's lemma, so we don't need to do it again, that if you have a chain of functions, the union is still a function, right? Because the chain means that all the functions kind of are compatible with each other. They don't, like, different functions don't give you different values on the same input. So you can put them together and it works fine. And we also prove, or I guess we just mentioned, but it's the same proof, that we also get it to be 1 to 1, same argument. So union of the chain is a function. What else? The range of a union is the union of the ranges. Yeah, so that's easy to see. And if each of these ranges are in the collection, they are all subsets of kappa. So the union of a bunch of subsets of kappa is still a subset of kappa. So that's fine. What about the domain? Well, the domain, we know that the domain is going to be the union of the domains also. And we know each of these domains is equal to the range union the range of each of the functions in the chain. And a union of a bunch of disjoint unions essentially is a disjoint union of the things in the bunch, right? So we're going to get that the union of all these disjoint union is exactly the disjoint union of the union of these guys, which is the range of the union of B, and the union of these guys, which is also the range of the union of B. So we get that the domain of the union of B is equal to the disjoint union of the range with itself, which is what we need. That's this property up here. So we got all the properties that we need to be a member of A. So we get that the union of B is a member of A because it satisfies all the properties that you need to be a member of this collection A. So that means that we have verified the chain property. Okay? Cool. So now if we verify the chain property, we can apply Zorn's lemma, right? Because we're in the hypothesis of Zorn's lemma, so we can apply it. And what does it bias? It bias maximal element in this collection, capital calligraphic A, right? So that's our maximal element. Let's call it F. Let's call it capital F to this maximal element. And now we have to see what do we do with this maximal element. It would be good if we had that this maximal element was a function from the kappa union kappa to kappa. But let's see what we actually get. What we get, because we know it belongs to the collection, is that the range is a subset of kappa, right? Because that's every member of the collection satisfies that. Let's call it A. Let's call it Roman A to this range of F. And also we know that since it's the collection, the domain of F is equal to the disjoint union of A with itself, right? If we knew that A was the whole of kappa, then we would be done. Because in that case, we'll have our bijection between kappa union kappa and kappa as we want to prove the lemma, okay? We know this function is maximal among all the possible functions. Does that imply that the union has to be kappa? So let's think about that for a little bit. Or could there be much left? Let me show you an example. Suppose here is kappa and A is just all of kappa without, so this one also is in kappa, without one element. And then here we have kappa disjoint union kappa, and it has two copies of A, and it has two left elements. Okay, so kappa has this thing. This one also belongs to kappa. And then we have two on the other side. Could we extend this function to a bijection between these two guys? But if you want to extend the function, you want to keep, we have our function f from here to here. We cannot change the values that it has so far if you're going to extend. Extend means preserve all the values that you defined already and add a few more. We can add one more, I don't know, we can map one of these guys to this one, but we couldn't map the two of them in a one-to-one way to this single element, right? So if you want to extend this function, keeping this fixed, just adding new things, we cannot increase A, because if we increase A, we have to add two elements on this side, but we'll only add one element on this side. And we're not going to get a bijection between this guy and this guy. Okay? So no, this is just wishful thinking. The maximal element need not have, or a maximal element need not have that the A is all of kappa. I mean, after we prove this, of course, there is a maximal element where A is kappa, but Zorn's might not give you that lemma, that maximal element. It gives you some maximal element. That's all it says. There exists some maximal element, and that one might not satisfy that it maps, or that A is kappa. It might miss a few things. Okay, well, 2 points. First, if what A is missing is just finitely many elements, let's say you're missing a few more. Let's say you're missing 3 elements up here, and on the kappa union kappa you're missing 6 elements, which you cannot match in any way. And you couldn't, no? If you add n elements on one side, you're adding 2 n elements on the other side. So you're not gonna be able to do the bijection. You're always gonna get stuck, and you couldn't increase anymore. It's not an issue though, right? Because this set A here, if it's finite, what we're missing, this set A will have the same cardinality of kappa, right? Because it's only missing finitely matched stuff. So we proved already that if you have an infinite cardinal, you're always equinumerous to a proper subset of yourself, right? And then that's equinumerous to a proper subset of itself and to a proper subset of itself. So if you just remove finitely many elements, it's the same. You're always going to be equinumerous to U minus finitely many elements. Essentially comes from that proof. Again, this requires a little arguments. Check it out or think about it. But yes, so essentially maybe what I'm saying here is that observation, if n is finite and I don't know, alpha is infinite, then n plus alpha as cardinals is equal to alpha. So this property about addition being the maximal is very easy when one of them is finite, right? You can just absorb it. And essentially is, remember that proof that we inside alpha we put an omega chain and then we move it all the elements and we leave n elements blank. Okay, so I'm not going to go into details on that one, but essentially what I'm saying here is that if kappa without A is finite, then we must have that A is equinumerous to kappa, and then we will have that kappa disjoint union kappa is equinumerous to A disjoint union A, because they are equinumerous, and that's our function f is a bijection between these and A by itself, which will be equinumerous to kappa. Okay? So in that case, if it's finite, it's not a big problem. So now the claim is that this has to be finite. So let's prove that claim. So for that, we're going to assume towards a contradiction that kappa minus A is infinite. And we are going to get a contradiction from that. So what do we have? Let's draw the same picture we had before again, but now with the infinite case. So now we have, let's say here is kappa, and now here is A, and what's left is infinite. And on the other side we have kappa union kappa, and here is A, and here is A again. And we have our function f that maps A union A to A, but leaves the rest untouched, right? And now, how is that we're gonna get a contradiction? And it's always the same when you're using Zorn's lemma. The contradiction comes because you have to contradict the fact that f was maximal. How you contradict that something is maximal? Well, you have to build or exhibit or show that there exists something that is bigger than this f. So we need to find an f that satisfies the properties of being in this collection, all these properties, that is larger than this f right here, that it extends it. Okay, so how are we gonna do that? Well, here's the trick. Since kappa minus A is infinite, we can pick an infinite subset that is countable and infinite. So in other words, D is equinumerous to omega, right? So we've done this before. We showed that if you have an infinite set, you can always have a one-to-one mapping from omega to it, right? So every infinite set is dominated by omega. We showed that before. So here is our set D, let's say, and it's twice because it's in the union, it appears twice, and in this side it appears once, right? But we know that D union, disjoint union D is equinumerous to omega disjoint union omega, which we know because omega disjoint union omega is 2 copies of omega, which is like the integers going omega both sides. That's equinumerous to omega. Just use the evens and the odds to make the equinumerosity, and then that's equinumerous to D. So there is a bijection between D and D union D, right? because of the numerosity. And then now, how are we going to extend f? Well, we know we have f defined already here, and now we have h that goes from these two guys to this one, so we put them together and we get an extension of f. The domain is now A union D, disjoint union A union D to A union D. So how do we define this g of x? Well, if x belongs to A union A, you use f, and if x belongs to D union D, you use g, right? And you get, from this case, you go through f, and in this case, you go through h. So now that f is extended by g. And also that g belongs to our collection of sets because it's 1 to 1, because both f and h are 1 to 1. The range and the domain have the right properties, so we made a bigger function, right? So this contradicts the fact that f was maximal, right? So it contradicts this. We get a contradiction because of the assumption that k plus minus a was finite, infinite, and then therefore it has to be finite. And we proved before that in the case when it's finite, then we still get a bijection between kappa union kappa and kappa. Cool, so that's the end of the proof. Let me just review the main steps. Main step was to apply Zorn's lemma, we need to define collection of families, and we are trying to find a bijection between kappa union kappa to kappa. But we're not going to ask that. We don't know if there is any because we're trying to prove. So instead, we just take functions from whose range is a subset of kappa and domain is the range union itself, but it has to be 1 to 1. One comment to make here, we have to make sure this collection is not empty. Why is it not empty? Well, the trivial function, the empty function is a function, domain is empty, the empty times empty is empty, and it's 1 to 1. Empty function is a member of here, so this is not empty class. And then there are two steps. First, verify the chain property, and then the next step is apply. Once you verify this chain property, you can apply Zorn's lemma, get a maximal element, and then you have to show that the maximal element gives you what you want. Well, it doesn't give us exactly what we want because we may have a few elements left that are not in the range of this function. But then the last proof we show that, well, if the elements that are left are infinite, then we could extend the function and show that it's not maximal. So the ones that are left need to be finite, and we observe that in the case when the ones that are left are finite, it's not an issue because at least said that the function that we are getting still has a domain and a range of size kappa. So we can use that one. So that's the proof. See you in the next video. We're going to show the same thing for times now.